All right, where did all this stuff come from? The model, forget the U term here. The model came from trying to figure out how a transistor works, so that the transistor that I got for a New Year's present, I can now use in the follow-up K computer, right? So if I'm going to compete with RIKEN, I'm going to have to start on a good footing. Then I'm going to have to go out and get a lot of money, right? But I want to know how my transistor works. Who told me to do this? I did. I made it up, or somebody did. Is there a reason for this? So I'm going to show you how, by reasoning about the process that we just went through, that this, or something like it, comes out automatically as a property of desiring to optimize the transfer of information from data to the model. And it doesn't depend on the fact it's a transistor or an atmosphere or a neuron. It doesn't require linearization. It doesn't require Gaussian distributions. Yes, sir?
Is it special that this term arises, or you write it in the equation for y1?
No, no. Suppose I had measured y2. I'd put it here, right? You can even be more creative than that. And,
Depends what you're mentioning.
yeah. I mean, I could have put this into this equation, but it wouldn't have had the direct effect on moving my model to the data as this one does. It would have an indirect effect at second order through the nonlinearity, all right? But I didn't want to make it, it's already complicated.
Henry, up there in the minimize you have a sum over indices, and below it's continuous. So
I learned from Sebastian Reich a couple days ago that you always think about everything in discrete time, but you write it sometimes in continuous time for convenience. So I give you the homework assignment of rewriting the differential equations in discrete time, because that's how we solve them.
So the n is the time index of the numeric method.
Oh, is that your question? Yes.
So you have continuous observations essentially.
They were pretty frequent.
Yeah, okay.
All right. You can go on and say, how frequent do you need to make the observations? Well, depends on the underlying instabilities of the nonlinear dynamics. All right. You can ask, at every time you make a measurement, how many measurements do you need to make? That depends upon the geometry of the instabilities. And I'm not talking about all that, right? This worked out.
Okay, because if you want to do this nudging, I guess you assume that your observations come in so frequently that's like on the level of the time step you would use for the
The criterion is that you have to measure more frequently than 1 over the largest Lyapunov exponent of the underlying system. And you can systematically, if you want, measure much more frequently, then less frequently, less frequently, less frequently. You can see that the cost function stays small until you're not measuring it frequently enough, and then it explodes to order 1. Yes, sir?
Is assimilate the training window of the same order of magnitude as the prediction window? Is that like, is there a correlation between?
There's nothing stopping you from having a very long prediction window. But in the case of a chaotic system, the predictions will get worse and worse and worse exponentially rapidly. And you have to tell me what level of accuracy of predictions you're willing to live with.
Right, but it looks like you have the training window of the same scale as the prediction scale.
Oh, I could easily have had, this is an overkill to show the idea. I could have had the observation window 1/10 the size in this particular case, and it would have worked fine. But I knew excuse me. Pardon my language. I knew a lot about the transistor. I have to admit it, I didn't have to learn it all. And, I'm sure you don't check all your transistors, of which you must have 10 to the 20th or something in one of these machines. Okay. Yes, sir?
Which particular term is responsible for leaking oscillation among these three?
Well, you're one of the people who had an undergraduate physics lab that somebody made you suffer in, right? So it's basically an RLC circuit.
Yeah.
So it's the LC is the oscillation. It's the energy being stored in the inductor versus the capacitor going back and forth.
Yeah, that I know, but I'm not.
That's the source of the oscillations.
But I'm not being able to relate to these variables with those LCRs.
That's because I didn't tell you the transformation from the actual physical variables to this dimensionless variables, because frankly, it's boring. All right, and I didn't think it illustrated anything. All right, so what I want to talk about is, where does this come from? Is this right? And if it's not quite right, which it is not quite right, I think that I say that in the next slide. Just for the record, this is wrong, but it works pretty well. And my view is, that's interesting, but I want to know why it works well and what is the right answer, and I'm going to derive that for you. And that's the tool that we use to study the neurons that were experimented with in Dan Margolish's lab, as well as some other things. But I'm going to try to focus on neurobiology. And at the end, whenever that comes, I am going to try to explain that exactly every word that I said about data assimilation in a physical system or a biological system transfers equivalently to machine learning. Machine learning is a statistical physics problem that everybody in this room has been learning about for the last week. Well, some of us for even longer than a week, right? All right, what time is it? 2 o'clock. Are we supposed to have a break? It's now? Let's have a break.